Recording is started. Okay. So now we are going to talk about communicating FSM. So I think you have some idea that to avoid complexity, to enhance to easily comprehend our complex design, we have introduced the concept of hierarchy. But when we are introducing hierarchy, that means we are introducing different types of different states, different machines who may be working together. So there must be some way, some technique how these machines, multiple machines, they should be communicating. For example, whatever we have discussed with this traffic light controller example, if you remember that, there we have talked about this traffic light controller. This was the model. Maybe you all have done this. There's something similar to this. And here we introduce some pedestrian input. And then we talked about that these pedestrian, pedestrian behavior, this that also we can model with some form of finite state machine. There must be some states we can define and some conditions to change those states. So that means these pedestrian is basically some output set by in a different FSM, and this pedestrian is coming back as an input to this FSM, to this this traffic light controller FSM. That means with this variable, these FSMs are communicating. Now today we will all talk in a more detailed way that how this communicating feature can be introduced and what more types of FSM combinations we can think of. So after hierarchy, here comes the concept of concurrency. That means if you think again back to this example, that pedestrian FSM as well as that traffic light controller FSM, basically both are running concurrently. So initially, if you think in most of the states, they are independent. When there is change from red to green or yellow to red, those things, everything is dependent on the counter or the timing associated in the traffic light controller. Similarly, there are some other state transition conditions defined in the pedestrian related FSM. So, but they are running concurrently, and within each state transition, they are generating some output that may be acting as input to the other one. So when we are talking about concurrency, let's take this example, E1 and N2. This is connected to this state B. Basically, if you are thinking this is a FSM where each state A1, A2, B, each state can be a single state or that can be decomposed to intermediate states. Here the example shows how this B can be decomposed to some intermediate states, that is C and D. Again, that C and D, those are getting decomposed to C1 and C2, D1 and D2. Now you can think that if we just focus on this B, that means you may think when you have a problem, you have a specification, now you are taking the top-down approach. You have identified the master states and now you are going in detail, detailed conditions, detailed requirements of each of the states. Okay, so here we are going we are looking into the state B. So here B is again can be decomposed to C and D. Now if we see C and D, the relation between the states C1 and C2, if we observe, and the relation between C and D, if you observe, are not same. Why? Here we are thinking that C and D, those are concurrent states. That means, that is, we may another term of that is and decomposition. What does it mean? That means simultaneously we are considering the output of C and D, or they are running parallelly. At a particular time, both C and D both are active, right? But now if we go into C or into D, and if we consider C1 and C2 or D1 and D2, now these relations are not exactly same, because C1, if there is some signal input or transition condition X, it is making a transition to C2. Similarly, if there is some input Y, transition condition Y is getting satisfied. Y is getting satisfied, C2 is making transition to C1. That means in this case, at a time, either C1 or C2, they are active. That's why this is called OR-decomposition. So when we actually map our complex requirements, so states, it is not that always we can actually get some definite small states. It may happen that we are actually defining the master states and then we are decomposing them to these substates, these types of substates. And those substates, they are maybe related to OR decomposition or maybe related to AND decomposition. Okay. So we will again formally come back into this mathematically, that how, formal relation, how the output of C will be when we know about some transition condition or state change details about C1 and C2. We will come back to it. Just now at this stage, just to have the idea that when we are decomposing, we may be decomposing to OR decomposition or maybe decomposing to AND decomposition. Now practically, when we are talking about this hierarchical FSM or we are talking about concurrency with that, those are defined in a tool, or that is defined in state chart languages. Okay. Now in that state chart, that is the first notion where FSM was extended with this hierarchy and concurrency concept. Okay. So in that state chart, there are some some extra constructs to make your design proper. That may be the requirement of your specification. Those are maybe you can think that those are very common requirements of your specification. One is timeout. Okay. So this is related to time limit. Another one is very important. I think timeout is very, if from the name you can understand, it is very easy to understand from the name. I'm not going into that. I'm going into the other construct that is very important, that is history. What do we mean by history? See, when we are thinking about decomposing some state through this hierarchy concept, if you remember, yesterday we have also discussed about the elevator example where we have shown that normal mode and the fire mode. That means from that normal mode, when the fire input is on, that you are coming to the fire mode. That was the concept, right? Now, when this fire mode is over, that means your fire on signal is off. Now there is no fire. That means again your elevator will go back to the initial state, normal mode. Now the question is, in this example, in elevator example, it may be very straightforward. That if you remember, in fire mode, we have defined that elevator came down in the ground floor, it opened the door, and that may be its initial condition. That state, that door opened and it is in the ground floor, that may be its initial state. But all specifications, you understand that all problems are not same. So that's why whenever you are defining some hierarchy, if this is, A1 and A2 is a state, and from there you are coming out to B by maybe getting this Z transition condition getting satisfied. Then again, due to some W input, W transition condition getting satisfied, you are going back to this state A. Basically, you are again making a transition back to A. So this is the convention of state chart, or it may be defined in other way, but I'm just talking about the convention, that to understand that again when I'm going back to A, where should I start? To maintain that, the concept of history is added. The concept of history is added. That means history is storing the last substate from where you have actually made a transition from A to B. That is the last state, left state. It may happen in some, when you will be using many tools related to these or many languages related to this, you may see somewhere history is maintained, somewhere it is not. That means somewhere a predefined initial state is maintained, like in our elevator example. Elevator example doesn't hold any concept of history, because wherever you do after fire mode, when you were starting from the ground floor. But in case of some other examples, it may happen you are holding the last substate where you left that master state, and whenever you are going back to that part, you are again starting from there. Okay. So this may be required. Can you give me one example where this may be required? Anyone? Anyone? Can you give me?
Ma'am, like it can be something like a very small task that needs to be executed periodically. So we execute that task, and after that task is finished, we return to a larger or a more important task that was being executed in the background.
Okay. So
In
where
that
is it?
case, so the task will resume from the point where it left off instead of
Yes.
starting again.
Yes. So in most common thing, maybe it was discussed in your class that you know the concept of interrupt to your processor. So what
Yes,
happens
ma'am.
when interrupt? What happens when any interrupt comes? When any interrupt request, some processor execution, some programming execution that is going on at that time. If your processor is getting some interrupt request, at that point of time, what happens? The processor stores the state of your process. Your operating system stores this, the state of your, so how far it has executed. That information it stores. That is the history. And when it services the interrupt, after that, it again come back, get back that information that where it left, up to which instruction it has executed, and from there it starts. So when you are modeling this type of maybe interrupt scenario, you can think of in the type of interrupt scenario, interrupt handling scenario, of course, that this history construct or adding this history concept, notion of history is very important. And whatever you have told, that is also correct. That you are talking about the preemption. In case of preemption, also history is important. So whenever we are actually modeling this type of scenario, history is actually plays a critical role. So far now this is our knowledge. We know whenever we have some complex scenario, we can divide to multiple FSMs, and we can arrange them into suitable hierarchy, like this normal mode and fire mode. In our elevator example, they are HFSM. You can think of that they are arranged in hierarchy. But if you think that unit control and request resolver, go back to if you do not remember, go back to our example that we have discussed, where if you remember, the unit control was associated with the general working of the elevator, And this request resolver was related to the when it is receiving request, maybe someone from outside the elevator who is requesting to get into the elevator, or someone inside the elevator who is choosing its floor, his or her floor, and to get out of the elevator. So where in which direction the elevator will go, where it will stop. So those things was maintained by this request resolver. So these two FSMs are basically running concurrently. So these, according to the that specification, these two, what to say, I can say blocks, these two FSMs, they are connected in concurrent way. But in normal mode, this fire mode, these two mode related FSMs, they are connected in hierarchical way. And that way, whenever you have arranged those FSMs according to your hierarchy and concurrency, inside each node, you can write the state changing conditions, map to your tool, whatever tools you are using. Based on that, you will actually choose the set of instruction, and it will write in that way. And this support is given by the state chart, which actually supports this hierarchy and concurrency model in FSM, and also enforcing this program state machine. That means you have added that state machine and you have the capability of programming. So program state machine. So again, if you think deeper, whenever you are thinking about this type of program state machines, there are two types of transitions possible. Actually, those are requirements. From these things are modified step by step based on the requirements generated from real life requirements. Now you think why these two types of transitions are required. In these two modes, in normal mode and in fire mode. Now, if your elevator is in normal mode and the fire mode is on, that time the transition will be such that in whichever state you are, you should jump down to this, level 0 or ground floor, wherever it may be, and open the door. So that is called the transition immediately transition requirement, or transition immediately transition, TI transition. Or if you are on the contrary, if you are in fire mode. In fire mode, whatever happens, if you are your fire mode was on, you just went to the fire mode, and now your fire signal is off. That means no more fire. That doesn't mean, maybe initially your elevator was at 15th floor, it was coming down to based on this fire input, and when it is maybe at the 3rd floor, the fire signal is on. That doesn't mean it will now work according to the request resolver. No. It will complete the whole instruction execution of that fire mode. That means that is called the transition on completion. And then once that is over, it will come down, it will open the door, and then when you again press, or someone again press the button, or maybe you, according to a specification, you give some idle time. So everything, that is how you are defining, how you are designing your system. But the main thing is that for some modes, for some type of transitions, we can come out from any states. No need to, maybe if that transition was done up to here, it may jump from here to here. But for transition on completion, that means transition will take place once you have executed, your system has executed all the possible instructions mentioned in that mode. So that is the concept of transition, two types of transitions present, supported in program state machine. Now we are coming to the practical level. So far you know how to model your system. You know that you have you can write the states, identify the states, identify the transition conditions. You can merge or split those finite states. And yes. Okay. The question is, now you know how to model those things with the use of state charge where you have defined hierarchy or concurrency. Now you know that what is it? You can model the system, add the history, timeout, all this concept. Fine. But when you are coming to now the implementation. Now, in this, basically, frankly speaking, in this course is a very fundamental course. So we cannot define in detail the different aspects of design. We have some other courses for that. But I'm just giving you some idea that when you have written this type of finite state machine, maybe you are defining a process related to that. So process means some program in execution. Now, when you are having some multiple hierarchy or concurrency concepts, that means you have just divided one state, you have divided one big state, maybe you can think one big process, to multiple sub-processes. Okay. Now for that, for the execution of those sub-processes, you may use the concept of thread. That is, those are lightweight processes that will take care of executing the, your execution of your sub-processes or sub-FSMs. Now, we have seen, if you remember your traffic light controller example, where the pedestrian FSM is giving input, some pedestrian input to a traffic light controller. That means there must be some communication, as we have talked, that when this concurrent or hierarchical FSM are going on, they are communicating through some signals or messages. Now, this is just a very basic concept that how two concurrent processes they can communicate. That means if we think now that you are having those lightweight processes, maybe process A and process B, that means you can map them small. See, process means always remember some program in execution. That means when you are writing these finite state machine in form of some program and you are executing this, that may be mapped to some of your process. Now, these multiple processes, now there is a requirement that they should communicate. So here are the two ways. This is a very required concept for understanding the communicating FSM, that they can communicate with the help of message passing or with the help of shared memory. That means in your processor, maybe some, in processor, the storage part is your memory. Now, some part of your memory, the most of the cases, for each process, they have their own memory. They fetch the data or associated files, everything from there, and they execute their program. But in case of communication requirement, there is a concept of shared memory where these parts can be communicated, that can be accessed by both process A and process B. So whenever any communicating FSM you are actually implementing, then you can take help of this shared memory where the information is stored in that shared memory. When process A completes and updates the pedestrian value, this shared memory value is getting updated, and maybe process B is associated with your traffic light controller and process A is associated with your pedestrian controller. So process A is writing pedestrian controller, process A is writing to the shared memory, and traffic light controller, process B is reading from that shared memory. So this is one way of communicating. Now there are different security issues. I'm not going into that. Let's consider as of now that there are two types of communication possibility. Another possibility is that process B is generating a message. M0, M1, those are different messages. And your operating system is maintaining different message queue. And with that message queue, each process B is sending a message to a process A. Let's see, this value has been updated. And process A in the next turn is actually using that updated value to use in the system. So this way, these two communicating FSMs, when they are actually implemented in the form of process, they exchange information and then work on the updated value. Okay, so this is the concept of communicating FSM. And most of the cases, when what we are talking about, that this implementation is taken care by operating system. I think you have this idea because you have already gone through the discussion of multitasking and real-time operating system, right? So there you have already seen that in multitasking scenario, you have multiple processes like that, and there you have, you have seen that the challenge you face, that how to schedule them, which process or which task you should schedule first or last, next, how will you set the priority, and based on that, how you will complete the scheduling process to maintain your real-time requirement. So that is, once we have just discussed from your specification how you can reach to the concurrent process, and when you are coming to that concurrent process in multitasking scenario in your real-time operating system, I hope that was already discussed, by previous professors, that after that how to schedule them, how to associate priority with them, and then execute them in your real-time operating system. Okay, so this is the basic idea about your hierarchy and concurrency and how you can introduce them in your FSM system model. Okay. Okay, I will formally talk about this more. Any questions so far? Do you want me to repeat anything? No, yes, nothing?
No, ma'am.
Okay. So that is the concept. We know that, we understand now how communicating FSMs are there. We have the idea that how we can implement them, and we know that if I want to communicate, where I should put my values. The shared resources shared in the shared memory, so that all the communicating FSMs, they can get the information. Now we will see, so in a very generalized way, that when we are talking about FSM, in general, whatever my specification may be, what type of compositions are possible. Maybe I have to handle what type of compositions. Okay. One composition, mostly once, since we have already discussed concurrency, you can understand that the one common composition will be side-by-side synchronous composition. That means here we are not thinking about communicating FSM. These two FSMs, they may be communicating to each other, or they may be giving output to some other third FSM here. Okay, not necessarily that they are communicating to each other. They may communicate, they may not. But the concept is they are side-by-side synchronous. That means this type of scenario where simultaneously A and B, both the outputs are important to you, and that is very deterministic. Okay. So, of course, to make your system deterministic, you have to understand your subcomponents will be deterministic. Okay. Now next come, when I have two FSMs, A and B, like here in the system. This is A, you can see this is A and this is B. You have two FSMs, you have some input given to them, and you are getting some output. Intermediate, some transition conditions are there. So how you will formally understand or formally model the state outputs. That means when you are thinking them as a combined state like this, This is your, as a whole, this is your combined state, maybe C. C is your combined state. And if you go into SIG, then you are getting two substates A and B. So we are going other way around. If we are fusing two substates, that means we are now going to bottom-up approach. Now we have separately identified component wise, maybe their inputs, output, their transition state transition conditions. But when we are looking at the CPS system as a whole or embedded system as a whole, what we need to do, we have to fuse the substates and make a bigger state and to get the idea of the gross view, right? So here we are defining state A and state B. Remember whatever we have discussed according to the basic definition of FSM, that finite state machine is a 5 or 6 tuple. Here we are just considering the basic, we are coming from the basic definition of finite state machine FSM, where we are considering the states, the inputs, the outputs, update, that means the transition conditions and the initial states. That's all. You know that when we have talked about extended FSM, these can be represented as a 6 tuple where we will be adding some added variable sets. But the modeling technique will be same. There is no difference. So similarly, we have defined B also with their states, inputs, outputs, update, transition condition, initial states. Now, when we are talking about the synchronous side-by-side composition, we have the states and state C, that is when I'm considering the combined master state, state C, that will be the states there will be the pair of states A and state B. Okay. And inputs also the pair of inputs A and inputs B. Similarly, outputs, only the initial states. For initial state, we have to consider all the initial state whenever we have fused, before combining all the states. And then the update condition. How this update means? Transition condition. How we are defining that? See, this update condition of C is defined with the states of SA and SB and along with their associated inputs IA and IB, and they are getting mapped to some states. That is general, right? Because whenever we are defining some state 1 to state 2 transition, we consider this is my update function maybe, and this is my output, and then I am moving to some output state. So there are two things. Output means actions that we are setting some output values, and this is the state. Where in case of synchronous, FSM side-by-side composition, we are updating both based on our some state A and input A, and some update condition, that is transition condition. We are getting some outputs states and output of related to state A. Similarly, we are getting on applying related transition conditions on SP and IB. We are getting a transition SP dash and OP. Okay. That means the main idea is whenever we are thinking about synchronous side-by-side composition, this is again AND composition. See, we discussed about and OR-decomposition, where we have to consider simultaneous effect of both the states or both the state transitions. So these are related by AND condition. Contrary, if we think about, I will come back to this. If we think about asynchronous side-by-side conversion, there the reaction is related by A or B. So a reaction of C is either coming from state A or state B, and most importantly, that is non-deterministic. the previous one is simultaneous and this is non-deterministic. That's why you can see how we are defining this update condition is same. In each cases, it is dependent on the states and inputs. But when they are related, we are just thinking that once we are updating SA and IA based on IA, and we are getting the states and outputs, either OB dash is absent, or if we are updating this one, OA dash is absent. So this is the basic difference. This part is the basic difference with the synchronous condition. You can see where these outputs SA dash and OA, they are related to AND condition, and here either one OA dash is absent or OB dash is absent. So these are the main concept, whether you according to your requirement, whether your underlying substates, either they are connected with synchronous way or they are connected in asynchronous way. Okay. Now let's go to this part. This is your A. See, you can see this is your A. These are having states S1 and S2, and B, you are having the states S3 and S4. Now you are combining, you are fusing these states and you are generating C. Okay. That means, again, by the definition, state 3 are you can form by pairing taking states from states A and states B. So the same thing we are doing here. S1, S2, S3, S4 means here we are considering S1, S3 to S2, S4 transitions, and here we have S1, S3 and S2, S4 transitions, or we are considering S1, S4 and S2, S3 transitions. And based on that, we are just considering these transition conditions. Okay. Similarly, if I go to this OR composition, as we have seen that that is not deterministic. So any of these transitions are possible. So that way, this part is non-deterministic, and we have to consider all possible transitions. Sometimes there is no transition. See, in this transition, there is no transition from S1 to S2. Just there is a transition from S1 to S4. So that is also possible, and that pair transition is also possible. So that way, this type of non-deterministic any transitions are possible in asynchronous side-by-side composition. So let's take one example. Maybe you can see this example. Here we are talking about two servers, okay, that can receive requests from a network. First, you just read the specification. There are two servers that can receive requests from network, and each request requires an unknown amount of time to service. Okay, so there is no that is not something definite that the way you can model specifically that when one server will finish the work and it can take the next task. So in that way, if one server is busy, you are maintaining one queue according to a specification, and the other server can respond to a request. Okay. So you can see here the same situation you are modeling. This is server 1, this is server 1, and this is server 2, server A and server B. Okay. So according to your specification, we have actually modeled these two states, idle and serving, and you are checking based on your transition condition what may be the possible transitions.
Excuse me, ma'am. In this case, yes. If A and B both are free, then wouldn't the task execute on both the servers together? Pardon?
Can you come again? Both are
like
free.
If A and B are both free,
yes.
Like then how is it deciding which?
Yeah, that part actually, this is a part of the part of the specification is given. Of course, there must be some predetermined rule that if A and B both are free, maybe in the initial condition, maybe the task will be getting started from A. There must be some rule, and then when A is busy, the task will go to B in that way. Okay, so this whatever we are working on, we are working on with some parts of the specification. Maybe that may be improved with some added conditions or requirements. So based on that, you can see that if one is idle, based on request, the transition is taking place to serving, and the serving state will be maintained until the request is not ending, there is no more request, and there is no more pending task. Pending task means that is getting added to your pending queue. Okay, and from that pending queue, each of the servers, they are fetching the task one by one, and they are processing. Okay, so this is one example of asynchronous composition. Maybe depending on a task, it may happen at a time, first maybe A is giving output, maybe next B is giving output. Then if the task is shorter, one bigger task is handled by B, and some smaller task is getting handled by A, it may happen A is giving output, then again B is giving output. So in this way, this is one practical example of asynchronous composition. Okay. So again, you understand that there is some concept of shared variables. That means specifically here the shared variable is the pending list or waiting queue, where you are actually storing the task. So whenever you are writing the codes or processes for these servers, handling server controller, then that pending queue should be stored in some shared location, so that both the server related to server controller code can access that. So this is one type synchronous. I hope you have got the idea about this synchronous and asynchronous composition. Next, compared to a simpler composition, that is the cascade composition or serial composition. As the name suggests, you can understand here is one E, another FSM B, and this is your master FSM when you are considering these states together. So A and B they're connected in a cascaded manner, serial manner, where output of B, see in this transition S1 is handling a self loop, and there by the input A, some input A, B variable is getting set, or B signal is getting set high, and that B signal is working as an input to this next FSM B. Okay, capital B. So that B is actually a transition condition here, and it is setting the output C. Okay, and C is your output. Okay, so this is the concept of cascade composition. I hope that if you again go back to this, think about your traffic light controller example. If we take the same example, so far you have seen that when we have talked about modeling the pedestrian behavior, we were very vague. We talked about that there must be some waiting and crossing states and some non-state, and there must some possibility of some non-determinism. But now we are trying to actually formally define one traffic light controller, where we are thinking about two states. One is green and red. When the green light is on, the traffic light controller is receiving. In general, it should be in a red state. That means pedestrians cannot cross. And when it will receive this cigar, remember from your traffic light controller, the same your assignment example. Here, when this yellow light was making a transition from yellow to red, that time your signal R, that signal was on. Okay, that was where your output. Now this output you are feeding now to this pedestrian light controller, where this is the transition condition. Sig R is on means now your main car related traffic light controller is in red state. Okay, So it is on means it is making setting this G, this pedestrian G signal high. That means this transition is going to green state. I mean, this traffic light controller is making a transition from red to green state. That means now the signal for the pedestrians are green and they can start crossing. Okay. Now when they are in the green state and there is counter, because you have to set some time relation, that sometime you have to assign that for this amount of time your traffic light controller will be on, I mean a green light will be on, so that your I mean what to say, the pedestrians can cross. Okay. So for that, this is an associated counter where you have set some timing value. It can be anything based on your specification. You have set this as 55. Anything can be there. So for that time, this traffic light controller will be in green state, and then when this count is over, it will set this sped R and it will make this condition, make this transition to red. Okay. That means now you can understand that if you have something, this traffic light controller, it is giving input, sorry, to your pedestrian controller, and it is giving some input that is sig R. Okay, that means they are connected in a cascaded way. You are basically cascading these two finite state machines, and this output of this traffic light controller, this one specific output is going to this controller, and that is set as the transition condition of this particular FSM. So this is one example of your cascaded composition or serial composition. Okay. So now again the same thing. Again, whenever you have this multiple, you are actually combining multiple substates to the one master state. You are combining all pairs of states, and that way you are defining the states of your master state. That means if you now see your separate states of your traffic light controller, these are the red, green, pending, yellow, green, red are from your pedestrian control. So now what you have to check, what are the possibilities. Here the possible state possibilities are red, 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 green, 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 red, and so on. So first thing you have to understand, you have to consider all the pairs when you are thinking about your combined FSM. And after that, you have to think about all the transition conditions from one state to another. For example, if you think here, see here, red-red combination to green-red combination. So here, red-red combination to green-red combination, right? Red-red, red-green. Okay. So for that, you have to check what is the condition to make a transition from red to green, and here the red is, it is basically the same from this red to that red. But one thing you have to observe, that when I think that is now maybe you are getting the point, that when you are considering all the states, see here some states are missing. For example, if you think that we have not considered this green state, if you see red, green, pending red, yellow, red, green, red, but no green. And some other few combinations are also there, is not there. The reason is that whenever you are cascading or whenever you are combining the states to go to the higher state, first thing you have to do, you have to choose the pairs. The second thing, you have to check whether all your state combinations are reachable or not. So you have to do the reachability analysis that we have actually discussed yesterday. So it is not that you are getting the pairs means you will actually consider all the pairs. No, you have to consider those pairs according to the specification that is actually reachable, and for them you will actually consider the transition conditions. Okay, so this is the concept of how we are actually thinking initially from our. There are two approaches. One approach is from your specification you are actually defining your master boxes, maybe I should say your master FSMs, and then you are splitting them in a smaller version. I think this part is quite comparatively easy when you have your master requirement and then you are defining the components and you are just defining their state transition conditions. That is one approach. Another approach is that when you are actually analyzing your design, your modeling technique from bottom-up approach, that you have actually got the substep. Now you are combining them and going bottom up, and you are checking as a whole, as a gross, whether that modeling technique is actually mapping your specification properly or not. And there also, if you consider all the states possible while merging, your state machine will be unnecessarily huge, that and some of the states in that part may be not required at all. In such cases, of course, you have to analyze these reachable states, which are from your practical point of view, you have to analyze these parts carefully, and you have to remove those unnecessary states, and then you have to draw your finite state machine. So that is the step by step what you can do, starting from your specification. Anything given to you, that based on that specification, you have to design one embedded software. So these are the steps you have to take care of. Okay. So whatever we have discussed, this is the summary. That in general, whenever we are going to, arrange our specifications, there may be two things. Maybe some side-by-side decomposition. Okay, that may be synchronous, that may be asynchronous. Based on that, you have to choose the output, and then you have some serial connection. Okay, so based on what type of specifications you have, you will design, place your blocks, and you will decide your composition. Okay, but one part, it is, you will think about it. Maybe after we discuss the hybrid system, you will get the answer of it. How you can think to resolve the feedback part, because that we have not discussed. That is one typical, it is very comparatively very simple to think of now, that if I can introduce some notion of time, that at time t, whatever my output, in the next time t, next t plus 1, I'm just considering that as my input. Okay, so that way I can actually resolve the feedback. Once I already connected all these parts, of course, feedback in our embedded scenario or control scenario, this feedback is very important requirement. But for that, we have to understand, how I will actually introduce that notion of time, because that is some continuous signal, and whatever we have discussed in our FSM so far, everything is event driven. I'm receiving one signal, and based on that, I'm defining the transition conditions. So how I will introduce, or how I will combine the concept of time continuous signal in my FSM, we will come into that. Maybe from there you will get the idea that how to resolve feedback also. Okay. So now again, another simple thing that we have discussed already. Yes, any question? Okay, let me finish this. Okay. that we talked about the hierarchical state machine, we also talked about the concept of history. Okay. Now, concurrency we understood. Side-by-side decomposition we have understood. Now, if we are going to decompose this type of hierarchical state machine, that means, see, this is my state machine, initial state machine, where I have these two states, A, B, and based on this transition G2, transition condition G2, if that is true, then my state will, I can make a transition from A to B. And if my state is B to A, I can make a transition, if my state transition condition G1 is true, I can make a transition from B to A, right? So it would have been simple if these are two simple states, but here we are thinking that B is not a simple state. B is basically fusion of two states. B is basically a state machine. We should say B is basically not a state, but this is a state machine where the intermediate states are C and D. Okay. So C and D means they also have their own transition conditions like G3, G4, and so on. Now, when we are actually going to decompose that, we are going to understand the underlying transition conditions in the sub-level. What will be our protocol, or what will be our assumptions? Because there should be few assumptions we should understand that is defined according to as a protocol, we can say. See, these are very straightforward. When we are from A to B, we are making a transition when G2 is true, right? So that means when G2 is true, we are going to B. And now if you see this symbol, this signifies this is the initial state of C. So it is given that when I'm entering in state B of a finite state machine, this is my initial state, C. I should always start with C. So this type of specification, this should be according to your specification, that whenever you are starting your FSM, finite state machine. Remember, in a finite state machine, in the tuple members, we already defined one member, that is initial state. So here C is my initial state. Okay. So from A to B, A to C, G2 is on, G2 is true, and I'm making a transition C. And that's why my action, I'm setting A2 as true. Okay. From C to D, that is the straightforward condition was G4. But here, one added condition is not G1. This is very important because if G1 is true, whatever may happen, that is the protocol, that is the rule, that if the priority of coming out from superstate to substate, that transition priority is always high. That means if G1 is sometime on and G4, both are true, it may happen in some cases both the signals are on. So then there is a possibility that C can make a transition from C to D, and C can also, there is a possibility to make a transition from C to A. Then which way C should go? And if we do not define it properly, then of course this scenario may lead to some non-determinism that we do not want, right? So that is a very defined rule that when G1 is on, the priority of G1 is always high, and the B should come out with any intermediate state and it should jump to B. So that means our transition conditions of our higher levels are, the priority of those transition conditions are always high. So that's why you can see, irrespective of G4, G1 and G4, or G1 and G4, or G1 not G4, in both the cases, C will make a transition to A. Doesn't matter whether G4 is on or not, because if that rule was not defined, that means C had both the possibilities to go to A or both the possibilities to go to D. Clear? That's why when you are expanding, decomposing, I should say, expanding your FSM to substates, and you are actually evaluating the transition conditions of your intermediate states, that in that part, this minus not G, sorry, this not G condition is very important, because not G is showing, not G1 condition is very important, because either that everything will, everything will go, in a way of non-determinism. Okay. So not G, again not G to D3, because if your FSM was in state D and at that time G3 is true and G1 is also true, at that time also you can see from D the transition will take place to A, not to C. So in hierarchy, this is a very important concept, that whenever you are in some intermediate state and both the signals are on, to make a transition in your intermediate substate or to go to your outer state. So always the priority of making the transition to outer state is high. So this is how you can think of a simple FSM with hierarchy, and you can decompose them. Okay. Is it okay?
Yes, ma'am.
Okay. So next quick topic, that is, you understand now, you have understood, I hope, that how you are arranging your different types of FSMs and how you are making the transitions from substate to superstate, superstate to substate, and if concurrency is there, what to do, how will you share your share your shared messages, everything. Now one question is, everything we talked about, one in terms of some discrete signal, maybe we should say discrete inputs. But when we are talking about cyber physical systems, and because embedded system is embedded system modeling means mostly we are trying to model the cyber physical system. They combine both physical dynamics as well as continuous dynamics. So in your modeling technique should be some some way that you should also be capable of modeling both of them. So how we are actually doing that modification, incorporating that modification, idea is completely simple, that here we are incorporating the notion of time. So whenever we are thinking about any continuous signal that is working in our cyber physical system as inputs or state transition conditions, we are just specifying, or we are just considering the value of it at particular time t, and according to that we are defining the transition conditions. For example, if we go back to our thermostat example, remember cooling, heating. That time we consider temperature as a discrete input. Here we are thinking that temperature as a continuous input, continuous in time t. So in that case, if when we are thinking about the temperature, we are specifically thinking the temperature, considering the value of a temperature of particular time, that at time t, and based on that we are specifying the transition conditions. So at time t, if the value of that continuous input is such and such, then according to that make the transition or do not make the transition. So that is called, this notion is called state refinement. Okay. So in case of state refinement, what we are actually doing, we are actually refining the dynamic behavior of outputs and additional continuous state variables. That means we are setting. If let's say this output, if you remember, we talked about for this transition, this is our transition condition, that is the guard, and this is output action, set action. That is the action we were talking about. Now this output action also may be continuous, but when we are making a transition, these guard, we are also considering the value of guard at time t, and we are setting the value of this action at time t. Okay, so with these and that way we are actually considering these states, all the states, a time-based system, but we are also incorporating the notion of discreteness, taking the value at particular time t. So that is called set refinement, and also setting action, that means setting the action values. So based on that, this is a very, common example. This is the most simplest example of hybrid system, that is designing the timer. Because you remember, so far whenever we have talked about in the traffic light controller also, when we talked about that, okay, your red to green transition will take after 60 seconds. There we have considered a counter. But basically, that is the notion or the concept of some time. So how we are considering this, how we are incorporating this time, that is, the time is a continuous signal in our timing automator. Here we are designing the timer. How? We are considering the rate of change of timer. We are defining that as our state variable input, and we are checking, this is our transition condition. For the timer, we are checking whether our timer has actually worked up to some time t. So if this is st greater than or equal to t, after that there will be tick. Tick may be your input to your actual modeling system. Maybe here, if you take the traffic light controller example, we can come here, or this one, thermostat example, that is, this is your at time t, if this is your temperature greater than 20, and you have said that at a particular state there may be some time your the thermostat should maintain a state for a particular time, that may be th and tc for heating and cooling states. So that means this time is greater than th and your temperature is greater than or equal to 20. In your state, you can see each time your timer, this is the rate of change of your timer, it is increasing by the rate of change you have defined. You may set it 1, 2, whatever, 1, 2, 5, anything. So by the rate of change you have defined, based on that, each state transition, the timer will change, and rate, that is the rate of change of your timer, and this is your total time that you will allow your state to maintain in that particular. That is the total time you maintain. You want to retain your thermostat in that particular state. So those are those concepts of time as well as temperature. Both, you see, both are continuous concepts, but at a particular time t, those are considered. So here we have combined the notion of discrete concepts, and with them we have actually defined our transition conditions. Okay, and that is based on that we are just doing the heating and cooling transfer. Transition between the modes. Okay, so this is the way. Initially we have just focused on that some discrete values. Now we are considering values of a continuous signal at a discrete time. That way we are incorporating the idea of continuous time, continuous signal handling in this event driven mode of modeling. Because if you remember when we started FSM, we will actually next class we will see some other types of modeling techniques. So far we have only talked about FSM, FSM and FSM. But when we talked about FSM, that is the most predominant one, because you are going to develop control software for the control. So that's why FSM is very important, but that is event driven. And in event driven modeling technique, we are incorporating combining the idea of continuous dynamics. Okay. So same way you can see that your traffic light controller example, there also you can modify this way and you can incorporate the concept of timer. Okay. So these are all about, I mean, a few concepts about FSM. Just let me know if you have any question or not. Any question? Yes.
I have a very basic doubt. Aren't most cyber-physical systems like microcontrollers, don't they work with discrete time steps? So why are we considering continuous times for those FSMs?
No. What I'm talking about, see, when you have the specification, right? You have one cyber physical system specification, and that you are modeling microprocessor, whatever you are doing, that is in your design part. After that it will come. You have not reached till there. You have only the specification. You are modeling now, and from that modeling you will go to the design part, because in the design part I will give some idea that what more you have to consider. When you are talking about microprocessor, right? There you have to choose that microprocessor, and then we will work with that. But now we are just in this modeling part, and in this modeling part, the modeling technique that is most suitable to you, that is finite state machine. But that works when there is some event occurs. When your event occurs, the state change will take place. So that is the concept. But that occurring of event, you cannot directly map with your continuous signals. But that continuous dynamics is a requirement of your specification that you must include in your, modeling also. That's why it is important. Okay, is it clear?
Yes, ma'am.
The microprocessor, that will come later, that will in the design phase. Any more questions? No one? Okay, I'm surprised that no one asked that which book, from which book we should follow or something like that. So I have uploaded the slide. You can see in the previous slide, there are two books mentioned. One book is by Frank Bahid, and another book by Lee Sechia. So these two books you follow step by step. There, whatever we are discussing, we are basically discussing from those two books. Okay, mostly. And anything else? No more question. Everything all clear. Surprising. Okay. Next day I will start with other models. So that's all for today. If you have no question, you may leave. Tell me.
Please upload these slides, lecture slides.
I've already uploaded. Just check it. Okay. I've uploaded.
Okay. Thank you, ma'am.
Okay.
Thank you, ma'am.
You know the location, right? I have shared that day in the chat. That drive folder there I have already uploaded.
Okay, thank you, ma'am.
Okay. So if you have no question, any other question, then you may leave. Okay. Start bidding if you have any question. And one thing I want to tell to everybody that I understand that you are from different backgrounds. Okay. Maybe sometimes some terms, if I'm from computer science background, some term is very obvious to me, but maybe that is not so obvious to you all. So then just ask me, or you can separately write in the chat box if some term you want to elaborate more. So then we will do. Mainly we will be discussing the modeling this part, but some part in the design maybe that may happen. Just stop me, ask me, or maybe you can write it in the chat and I will explain it. Okay, because I'm assuming some term that is very common, so I'm not maybe explaining, but that may create problem to you. It will happen because you are from diverse background, so maybe that thread term, I was expecting some questions from you, because the thread is maybe you have, whoever done this programming and data structure lab, you have used that some compiler or something, but otherwise it is not known to you. Anyway, so if you have any question, any term related question, just stop and ask. Just make me stop and ask me. Okay, that's all. You can leave. That's all. Just go through the chapter slides. Whatever doubts you have, then ask me.
Thank you, ma'am.
Thank you. Thank you.
Thank you, ma'am.